Good morning. I'm Dr. Sanjay Jain, Associate Professor in Mathematics at SPC Government College, Ajmer. Today we are talking or taking lecture on differential geometry. Earlier we have taken few lecture on differential geometry. Today we are taking some definitions related to differential geometry and important for differential geometry. The very first definition we are taking is the normal plane to the curve. Actually, or earlier, we have studied where is the coordinate geometry. We know that tangent and normal are perpendicular to each other. Using this fact, what we have defined here, because we need normal plane, so we are considering a plane through P which is on a right angle to the tangent at P will contain normal to the curve, and so is called normal plane. What is the meaning of this? Any curve R equals to RT, any point we have on this, and a plane passes P through P which is right angle to the tangent at P will contain normals to the curve, and this normal to the curve is called normal plane. If we are taking a Cartesian coordinate system or axis or rectangular equation, then the equation of normal plane is very simple, or we have already studied it. It is nothing but capital X minus a small x and x dot means first differentiation of x plus y minus y and y dot differentiation of y with respect to first differentiation plus z minus z dot or first differentiation of z is equals to 0. The coordinate are x y z, small x y z are the coordinate of point P, and x dash y dash z dash are the first differentiation. Okay, so now this equation x minus small x into x dot or first differentiation of x plus y minus y into y dash plus z minus z into z dash equals to 0 is the equation of the normal plane. So if we are given in a Cartesian coordinate system any point P, then we can calculate the normal plane at the point to the curve. So this is the normal plane of the curve. Second definition we are using is order of contact. What is order of contact? If a curve, let's say r equals to rt, any curve, if a curve and a surface, so what we are taking here, two things we are taking here, curve and surface. Okay, curve is a two-dimension figure, surface three-dimension. So if a curve and surface have a certain number of consecutive points in common, then they are said to have contact of certain order. If what is the meaning? Some point common on curve and surface meetings point, or we say they are common point, having some content of certain order. We here we can't define any order. Okay, now we define order of contact. This is just we defining what is the meaning of order of a contact. Here you are seeing some diagram in the blue. uh, what we are seeing here, by the showing red dot that is on any point P on the curve. In the first diagram, we are seeing that the red point having two arc passes on the red point. In the second diagram, only a red point having a one arc. But in the last diagram or third diagram, we have a red dot passes three different curved lines on this. So in the first diagram, having two contact point. In the second diagram, we have only one contact or passes only one line. In the third, we have three different arc passes through a point. Similarly, from a point, it may passes many lines, so we can go up to n order contact, may finite, may infinite. So here we defining the order of an contact by giving some simple idea of by the diagrams. Okay, if p0, if p1, p2 and so on up to pn points of a given curve lies on the given surface, means curve and surface having n points common p1, p2 up to pn coincide with the point P, coincide tends to point P or coincide with point P, then in the limit when p1, p2, pn coincide with P, the curve head surface will be said to have contact of nth order at P. N point tends to a single point. That limiting positions have to set in a contact of nth order at P. This is a general definition for nth order. If there are 3 points, it is on a 3 order. If it is on a 2 point, it is on a 2 order. If it is on a single point, it is on a 1 order. So we are taking limiting positions of the n points when tending to a point P is known as contact of order at P. In next part, we are seeing how much order or mathematically the condition for which order of contact exists. In the next slide, we are taking order of contact between curve and surface. Here we want to find how many numbers of order of contact between curve and order we have. What we are doing here, consider a curve C and surface S, taking their mathematical definition x equals to ft, y equals to zt and z equals to ht be the curve, and f of x comma y comma z equals to 0 the surface. So we have a curve C and surface S. The value of t corresponding to the point which are common to C and S are given by the solution of equation obtained from 1 and 2 on eliminating x, y, z. Okay, what we are doing, eliminating x, y, z towards t, so it becomes, we are putting the value of x, y, z from equation 1 in terms of t. We get f equals to ft comma gt comma ht is equal to 0, or in one parametric variable we can say ft equals to 0. Okay, let t0 be the one of the solution of 3, or as we seen in the earlier slide that all the nth point tends to a point P. Here we say let T0 the one of the solution means all the point tends to T0, then it must satisfy then it must satisfy uh, Ft equals to 0. T0 is the solution, then it equals to Ft0 equals to 0. So using Ft equals to 0, we are opening this point Ft equals to 0 using the Taylor theorem in power series terms of t minus t0 because it's tending to t0 point. So we get ft equals to ft0 plus t minus t0 f first differentiation of t0 and up to tn we get the term as we are seeing here by using of the Taylor theorem. Okay, what we are getting here, the ft in terms of differentiations f dash t, f double dash t and up to f and t. Okay, now we have already seen if t0 is the solution, so ft0 is equal to 0, so the first term of the equation ft0 is a 0, so we get ft equals to, by putting ft0 equals to 0 we get ft equals to t minus t0 f dash t0 plus t minus t0 whole square over factorial 2 f double dash t0 and so on up to t minus tn whole raised to power n over a n factorial f and tn and so on. So this is the term we are using for the order of contact. How we get order of contact by this last term we are seeing in the next slide. Okay, what we are seeing in the next slide, this is an important. There are many cases we are getting here. First, if f dash t0 is not equal to 0 means the first term can't becomes 0, then t0 is a simple 0 and ft, and in this case cns said to be have simple intersection. Okay, because f dash t is not equal to 0 means first term can't become 0, it is in a simple 0 and simple interactions means it's touching simply. Second case, if f dash t0 is equal to 0, first term should be 0, first differentiation at t0 becomes 0, but second differentiation at t0 is not equal to 0, then t0 is double 0. t0 is called double 0 of ft and the curve C and S have 2-point contact or contact of first order. So please see the difference here. Point of contact is 2, but order is first. Okay, means if we have an n plus 1 point contact, then contact of order is n. Okay, so order is always less than 1 with the point of contact. Okay, if second differentiation is not equal to 0, it has 2-point contact but order is first. Now in the third case, if first differentiation and second differentiation is 0 but third differentiation at t0 is not equal to 0, then t0 is triple 0 of f dash t, ft, and curve C and S have 3-point contact and order is less than 1, so order becomes second order. So we generalize it up to n order, then we can write ft0 is equals to f dash t0 is equals to so on f dash fr t0 is equal to 0, but fr plus 1 t0 is not equal to 0, then c and s are said to have r plus 1th point contact or contact of rth order. Okay, so the term, let's say f and t0 is not equal to 0, then it is an nth point contact and the order is n minus 1th order. Okay, so this is the many cases we can get from the last term of the last slide by using which terms are 0, putting these terms 0, and remaining term shows point of contact or order of contact. So these two slides are very important: order of contact between curve and surface, how we get the last equation by using 0 1 by 1, we get different cases, and these explain the order of contact. Okay, now we are going for the last definition, point of inflectional. You are also going from this point of inflectional in the singular point. When you are reading in first year or second year calculus, what is point of inflectional, you are already studied it. Here what we are doing, we are taking a point P on the curve r equals to rt, is called point of inflectional at the point if the second differentiation d2r over ds square, s is what, arc length. Okay, so d2r over ds square becomes 0, second differentiation of r at the point P with respect to arc length becomes 0. This implies, or we say, r double dash 0 or r double dash at s equals to 0, and tangent at that point is called inflectional tangent. Okay, so condition is that second differentiation becomes 0 if at that point, then the tangent of that point is called inflectional tangent. This is in the term of polar form. Okay, now if we have a Cartesian coordinate system, then we are using, if fxyz be the any point on the surface, then the equation of the line through P is x minus x1 over L equals to y minus y1 over m equals to z minus z1 over n is equal to t. This equation, the inflectional tangent are the tangent which have 3-point contact. Okay, now you can understand the inflection tangent in terms of point of contact. So if any 3-point contact on the point, then the tangent is called inflectional tangent inside the given surface where t equals to 0. So we can say 3-point contact or order of second order contact. Okay, so this is point of inflectional or inflectional method to find inflectional tangents. Okay, so today we are stopping our chapter here. You may revise these definition. In the next turn we are taking some numerical example on these definitions. Thank you.